In this video, we're going to continue to look at high energy compounds found in metabolism. In the last video, we talked a lot about ATP, and we're just going to finish up on that subject right now. I said in the last video that when phosphates are lost from ATP, they are usually transferred onto something else, but they don't always have to be. There are some examples like that we covered in Biochemistry 1, such as muscle contractions, chaperones, transmembrane active transport. When they use ATP, they just burn it. They will be in the enzyme, and the phosphate isn't transferred to anything. It's basically transferred to water, more or less, or it's just floating around the cell. Since the phosphate's not transferred, these processes are irreversible. You can't put the phosphate back on if you didn't transfer it to anything. It's just lost. Now, as I said in the last video as well, this is a very slow process. Even though that delta G is negative, delta G double dagger, which is the delta G of the transition state, is very large. Therefore, this reaction is very slow. We call this thermodynamically favored, but kinetically disfavored. So that's supposed to say but there. That means that even though it's very negative, delta G, that does not mean that it actually happens fast. And I want you to remember that point. Just because delta G is negative does not mean it will happen in your lifetime. It just means that it is spontaneous at some point. And we've been talking about cleaving off one phosphate. You can also cleave off two phosphates at once, PPI. We call this pyrophosphate. So if you're cleaving two phosphates off at once and they're still connected, that's a pyrophosphate. And we see this for tRNAs and amino acids, or when you're making nucleic acids, you will use pyrophosphate. Now, although ATP is ubiquitous in the cell and all cell types, other high energy compounds are used in metabolism as well. So anything on this chart that is above ATP has more energy per phosphate than ATP does. One thing that these compounds can do is help maintain the levels of ATP by remaking ATP. ATP in your body has a half-life of seconds to minutes, and in your brain, the amount of ATP you have isn't that long. It's maybe a minute and a half or something like that. That's why your brain is the first organ that's damaged when you don't have oxygen. And if you're just at rest, you will use roughly 3 moles to 1.5 kilojoules or kilograms of ATP per hour. So we use a lot of ATP, and so we need to remake it. One of the ways we can make it is called substrate level phosphorylation. That is, taking phosphate from these high energy compounds and giving it to ATP. And all these enzymes that will transfer phosphates around, we call them kinases. A kinase is an enzyme that will transfer phosphates, usually from ATP. Now, if we look at these high energy compounds, the reason they're high energy is because they actually have worse resonance structures than ATP does. So we can look at just an example here of phosphocreatine and phosphoarginine, where they have the C double bond N, NH, P double bond O. Now, to make a double bond here with this resonance structure, you have to use one electron. That means that you'll have a nitrogen that's a radical. That will not be good. While your nitrogen and oxygen wants to be neutral, oxygen wants to be negative, nitrogen wants to be neutral. So you want to form these double bonds, but this nitrogen doesn't want to form the double bond, so it's very high energy. While low energy compounds have great resonance structures. So glycerol 3-phosphate, glucose 6-phosphate, they don't have the problems that your ATP does or your acetylphosphates do when it comes to resonance structures. So they're lower in energy. Now, talking about phosphocreatine, if you've gone through the health food area of your supermarket, or where they keep all the health pills and powders and what have you, you might have come across creatine. And the reason they sell creatine in a big old bottle like this is because in your muscles, phosphocreatine will regenerate ATP. and also does it in your nerve cells. So the reaction is ATP plus creatine makes phosphocreatine plus ADP. And so this can work backwards, where you have phosphocreatine plus ADP to remake ATP. So under standard conditions, this is not spontaneous. So ATP and creatine will not react under standard conditions. However, in the cell, phosphocreatine and ADP are low, so this does make it roughly a delta G of 0 when you take into consideration concentrations. And this is actually kind of like a buffer for the amount of ATP in your cell. So let's say you're not really exercising, you're not moving, your ATP concentration in your muscles is high. Since it's high on the reactants, you're going to react with creatine to make phosphocreatine. But let's say that you start working out or you start running and you're using your ATP, you have low ATP. So phosphocreatine will actually work backwards to remake ATP. It's kind of like an ATP bank or buffer, this creatine, way you can remake ATP or store it for when you need to use it. Now, we've been talking a lot about ATP, but there are different nucleotide TPs in your body. You have CTP, GTP, UTP, and TTP, and they're used for other processes. For example, RNA synthesis needs C, G, U, and ATP, while DNA synthesis needs DC, DG, DT, and DATP. Remember, this D means deoxyribose, so if there's no letter in front of ATP or CTP, that means it's RNA form. And interestingly, all nucleoside triphosphates are actually synthesized from ATP. So to get these, you need ATP. And the enzyme that does this are nucleoside diphosphate kinases, where you take ATP and the nucleotide in your DP form, and you just take a phosphate from ATP and put it on this nucleotide. Delta G is roughly 0, so this can work in reverse, no problem. But the way that this moves to the products is that when NTP is created, it's used by one of these processes. So the other NTPs in the cell are kept low, so you're going to keep making these NTPs. Now, some kinases in your body are simply work doing a kind of weird reaction when you think about it, but it's taking AMP plus ATP and just making 2 ADPs. And this can work backwards as well. The enzyme that does this is called adenylate kinase, or adenylate kinase, and this is found in all cell types in your body. And the reason for this is that you want AMP, ADP, and ATP to be at certain levels. If they're at different levels, different enzymes can't work, or enzymes are turned on or turned off. So you really don't want to mess with these ratios. So this enzyme simply restores the balance of these ratios. And the way it generally works is that you bind AMP and ATP in the reaction site, and then to prevent water from coming in and just hydrolyzing your ATP, rendering your reaction useless, you have a 230 residues, kind of like a cover that just goes over your substrates to exclude water. Then these substrates are close to each other. You have the transfer of the phosphate to make 2 ADPs, and then you release your ADPs. So one other compound we need to talk about is our bioesters. These are thought to be like the first energy compounds ever for life, because phosphates are scarce, especially in a world that didn't have much life to begin with. Having phosphates around wasn't really a thing, so early life adopted a different type of energy currency, the bioester. And this is actually in all central metabolic pathways of all known organisms use this bioester. The common form you're going to find and we're going to talk about is acetyl-CoA, which is shown here. Your acetyl group, your beta-mercaptyl ethylamine residue, pantothenic acid residue, and your adeno-3 phosphate, all connected. So these are energy. They're also a carrier of acyl groups. You can put different acyl groups up here, and you can carry around the cell and do chemistry with your acyl groups. And when you hydrolyze this bond, you actually get more energy than ATP. roughly 1 kilojoule per mole more energy. And these thioesters are much more energetic than a regular ester because if you look on your periodic table, sulfur is much bigger than oxygen. Therefore, when you put a sulfur next to a carbon, you don't have much of an overlap of your orbitals. Since you don't have much overlap of your electronic orbitals, you can't have a good resonance structure. Resonance structure is generally lower energy, so if you can't have a resonance structure, this is a high energy bond that you want to break, and so that's why it's more energy than phosphate. All due to resonance structure and size of atoms. Going back to basic chemistry right there. And that is it for this video. I will see you in the next one.